stop talking to myself here in a minute. So let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you bless our work today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. So, let me... Oh, I guess we're supposed to top hat, huh? I better do that. While I'm doing that, let me hand a sheet out to you guys. So what you want, there's two things in here that you want. So the one is the sheet that's got these squares on both sides. So you want one of those, and you also want one of these guys. All right, and so you should have basically like 3 total pages. So I'll start it here. Just you're the lucky one. You've got both. So show her so she knows what she's looking for. They want those two. Don't worry, we won't get to that point in class for about 10 minutes. So if it takes 10 minutes for it to work its way around, it's gonna be okay. But we're talking about graphing today, so I think those worksheets will be helpful to us. All right. So, of course, you'd like to top hat. Well, maybe. I'm not sure you'd like to, but we better do it. Let's see here. 4675. All right. So we're talking about graphing today. And so to start with, what I want to talk about is the excuse me. Beware of the wild cards in there that are like the ones I have single-sided printouts of the originals. They're in there somewhere. Those are the ones you don't want. So you're looking for the sheet with the squares on both sides. All right. All right. So let's talk about. Oh, you got it. I mean, the thing is, do you have all the pages though? So you need the real version of this is what you need, right? These were all in order before I got to the other 3 sections, and then these papers got all scrambled. Let me steal one of those. Thank you. Okay, so what is a graph of a function, right? Do you guys remember? So, just to be clear, if we have, technically speaking, the graph of a function, it's a set of ordered pairs, right? X comma y such that what? Such that x is in the domain of the function. And what else? Y is equal to f of x, right? So, really, mostly we just focus in on what? When you think about a graph, you really just want to focus in on this piece right here. The graph is the set of x and y such that y equals f of x, right? So how do we create a graph for a given function? So let me look at a specific example here. All right. And so example 1, we'll look at f of x, and we're gonna do something called a case-wise defined function, because you guys need a little bit more practice with that, right? Maybe you're not comfortable with this concept yet. So how about this? We'll have 3 minus x, and this will be for x less than 2, all right? And then x squared minus 1 for x greater than or equal to 2. All right, I want to try to graph this function, okay? So how do you do such a thing? Well, the first idea is just to make a table, right? And to find the values, right? Make yourself a list of points that you can then put on the graph. So we'll make this table. We'll put an x here, all right? We'll put y equals to f of x over here, right? So in this case, right, like that. And then finally over here, we'll put, the point that we get from that, all right? Now, in making such a table, you really have you have a lot of freedom about how you make the choices in here. So I'm just going to pick, I don't know, about 6. I think if I do about 6 for this example, we'll probably have a pretty good sense of what it looks like. All right. And okay, so I'm going to start at, say, -1. Then I'm going to go to 0. I'm going to look at 1. I'm going to look at 2. I'm going to look at 3. And we'll do that much. All right. And we'll look at the graph, and if we need to do more, we'll add some more, okay? So, all right, so if you're if you're looking at x equals to -1, right? And your function is this case-wise defined function right here. How does that work? What does this mean? Sometimes instead of this, you'll see like sometimes you put the word if here, You could do that. That's another notation. I like to put colon usually, but so my question is, which case are we in at -1? X is less than 2, right? X is less than 2. So that means that we're in case 1, right? So we'll do 3 minus a -1, right? Which is going to be 4. So what point do I get on the graph? I get the point -1, 4 is a point on my graph, right? Okay, next, 0. Which case is 0 in? Well, 0 is still in case 1, right? I'll circle. This is case 1, right? This case right here. So still we're there. So 3 minus 0 is 3. And so that gives us the point 0, 3 on our graph, right? X goes in the first, Y goes in the second. How about 1? Which case are we in for 1? Well, it looks like we're still in the first case, right? So 3 minus 1 is equal to 2. So that gives us the point 1, 2 on our graph, all right? What's up next? 2. Wait a minute, 2. Hey, 2, that one, now, finally, we've made it to what? The other case, right? Because it's 2 is greater than or equal to 2, right? So now I have to use the other formula, right? So I do 2 squared minus 1, right? Which is 4 minus 1, which is 3. And then when I go to 3, I'm still in the other case. 3 squared minus 1 is 9 minus 1, which is 8. So I got myself the points 2, 3, and then 2, 8. All right? Yep.
How did you know to start the other equation?
Because it's a case-wise defined function. So the question is, which case are we in? Right? The input is x. So here, x is equal to 2. 2 is greater than or equal to 2, so I'm in this case.
Okay.
Now this one, 3. 3 is greater than or equal to 2. Oh, goodness gracious. No, thank you. That was typo. My bad. Is that what you're asking about?
No.
Okay. So I think we have enough to make the graph, actually. This is probably enough, all right? So let's do it. So I'll make it nice and big over here. Let's see here. I probably can't commit to the same scale on the x and the y here. Yeah. So before I get too carried away here making the graph, an important thing to do before you just go headlong into making the graph is to take a look at your data, right? And make sure that you're choosing a scale where you can make the graph nice and big and pretty, right? A lot of times I see students do this thing where you just make the graph have like a convenient, maybe one box per unit or something, you know? And you choose a scale for your graph, right? And then you got this big piece of graph paper, and your whole graph is this one tiny little thing, right? A little postage stamp on this giant sheet of paper that you've just wasted. So to avoid that, it's important to take a step back and look at the data that you're graphing before you do it. Now here, I'm going from -1 to 3, so that gives me a sense of what I want for x values. How about the y values? They're ranging from what? From 2 to 8. So you see, I've already kind of wasted space on the board. Let me fix that. Because what? I don't really need all that real estate south of the x-axis, do I? Not really. So instead of that, why don't I do like this? That way I can do better. All right, so I'll use my handy dandy finger length units here. I don't need that many, obviously. Let's see here. Probably should use a bigger. All right. Obviously, if you had graph paper, that would be convenient, yeah? Let's see here. So I'm going from, I'm going to try to make this 1, 2, 3, 4, 5, 6, 7, 8. All right. And let's see the other way. 1, 2, 3, -1, -2. Actually, I think I'm going to go ahead and add a -2 to my list here, just to make my life a little bit easier. -2. So what -2 is in which case? The first one, right? So I got 3 minus a -2, which gives me 5, right? So I have -2 comma 5 is another point, and you know what? I'll go ahead and throw in -3 while I'm at it. 3 minus a -3, which is 6. So I've got, -3, 6. All right, great. Okay, so there we go. So now what I'm going to do is graph these points. All right, so let's see here. -1, 4, where is that? So -1 is here. X is -1, right? Y is 4, so that's about right here, right? That's -1, 4. 0, 3, where's that? Well, that's the y-intercept, right? So that's about right here, right? 0, 3. 1, 2, where's that? Well, it's about right here, right? -2, I'm going to do the -2 one. -2 is at -2, 5. So it's about right here. And -3, 6 is about right there. Okay. Now, what happens here at 2? At 2 we got what? We've got 2, 3, right? So at 2, we go 2, 3. So that's about right here, right? And at 3, we go 3, 8. So that guy is way up here. All right, so I'll label that point. That's 3, 8, for example. Right, this one here was 2, 3. All right. So, and now we just have to use part of our, common sense here. What are we dealing with for x less than 2? What is this graph, actually? It's a what? If you have y equals 3 minus x, what are we dealing with? It's a what? No. Y equals 3 minus x.
Oh.
What is it? Let me write it out. You guys know this. What is y equals 3 minus x? If I had that on the test, if I had asked you, yeah, this is the slope, slope-intercept form of a line, right? The intercept is 3, the slope is minus 1, right? It's a line. Now this graph is not a line, not altogether, but the first case of it is, right? So you know how to graph that, right? So I figured out that's what this is for. See here, I can do it again. Yeah. All right, here we go. Oops. See, my inability to get the coordinates right showing up here. So there you go. So if you have a line, I recommend finding a straight edge for better results, right? If you have a ruler, it's nice. Now here at 2, we have a what? We have one of those open circles, right? Because the value of the function is actually defined to be f of 2 is 3, right? F of 2 is equal to 3, right? F of 2 is not 1 like the line formula says. Okay? That's called a discontinuity in the graph, right? So this line keeps going and going, right? And then now you said parabola. That was right for the other case. So this is indeed a parabola. It's a parabola that opens up, and it has a y-intercept of minus 1, actually. So in any event, it's to here, and then it rather quickly goes all the way up to there, right? So up to the limits of my... It's hard to see the proper arc to it here, but if you could trace that back past its origin, it probably is not even that. It's pretty steep the whole way. See, because it's coming from basically here. This is not really, if it traces back to minus 1, that's where it's coming from. So this is not. Let me just. I'm drawing that there for a second. Look at it. I'm not going to erase it because it's not the graph we're graphing. I'm just saying, in principle, you could trace back. If you were to just keep graphing this formula here, it would be this parabola, all right? But we just picked the story up there at 2 and go on. This is, of course, not that case, right? The line is that case, so we don't graph that over here. But, of course, you could do this whole... If you understood how to graph parabolas and you were confident about that, right? You wouldn't have to go and make this table of values, right? You could just graph the line on the left, and you could graph the parabola on the right, and just put them together, right? You don't actually need to make... Because what time is it? This is not like some kind of like political statement about you coming late. This is like something I always ask at this point in the lecture. So just so you know, I'm not being like snide. I mean, I might be snide, but not about that. So it's 8:39, right? How long have we been here? 25. Let's see, 8:15. 25 minutes. 25 minutes. Well, I was late too, so make that 20 minutes, right? So for about 20 minutes, we've been doing this. That's a lot of time to make a graph, right? This method is what? Painfully slow. Do you agree? So is there a better way of making a graph? The answer is yes. That's why I've given you those worksheets. All right, so we're going to learn a better method for making a graph called transformations, graphing by transformations, all right? Now, before I even do that, I think we should spend a couple minutes looking at technology and graphing, all right? So let me do that next here. And then we'll come back to those worksheets. Any question about this? So if you want to make a graph, you can do this, right? You make a table, you plug in the numbers, you create pairs of points, you put them on your graph, you play connect the dots, you got a picture, right? We can do this. Do we want to do this? I mean, I don't want to do this. Not too much. But it is, the skill that we're seeing here, it's an important thing to be able to fall back on. If you're, as you're graphing with the other methods, you want to add a point to make your graph better, you always have to fall back on these ideas of just plugging it in, looking at what is y when you plug in the x, right? Like, it all comes back to this. If you want to add a point to your graph, you need to understand how to create points on the graph. X goes in the x, f of x goes in the y, right? It's just that. Of course, the wrinkle for my example is that it's, you know, the case-wise defined function there. All right, here we go. All right, so let me get the screen down here. So some of you have graphing calculators, right? None of you can use them on the test, right? But I would encourage you, actually, for the sake of graphing, what's even better than a graphing calculator are certain modern websites. In my opinion, chief among them at the moment is what's called Desmos.com. Desmos.com, come on. You can graph all kinds of stuff, all right? So eventually it'll show up. I think I've got the right source. I mean, yeah. Oh, there we go. So, all right, let's start out real simple. Y equals x squared. What's that look like? There it is, right? Simple as that. Y equals x squared. Now, what if we want to explore? We want to see, what's this look like if you add a constant? I can add what's called a slider, like that. And now I've got a constant which I can adjust. I can make the graph go up. I can make the graph go down. So looking at your, where did the extras of the handouts go to? Did everybody, some people came in. Did you get it yet? Make sure you got one. So you guys look at number 1 on the transformations sheet, right? What I'm doing right now is illustrating, hand that back to her, thanks. Everybody else got them? Oh, yeah, no, you're fine. Everybody, so I need you to hand that back, and also this one, thank you. Make sure you top hat. We'll top hat 2 times today because we're doing this worksheet. So there's extra participation today. But my point to you guys is, look at transformation number 1. I say if you add c and it's positive, what does it do? See, if it's positive, let me put it in the reference point here. Let's put in y equals x squared. There's the base case in red, okay? And now I'm making c positive. See what's going on? It goes up, right? If I make c negative, what happens? It goes down, right? And you can also do this. Whee! All right, I'll stop. Now, what would happen if instead of adding c, let's say I add b, let's say. Add slider b. All right, so what happens now if I adjust b? If I make b positive, see what happens? The graph goes to the left, right? Incorrect. If I make b negative, what happens? It goes to the right. See that? So replacing x, substituting x plus b in the place of x, moves the graph to the right if b is negative, and it moves the graph to the left if b is positive. I know that's counterintuitive, but that's just the way it works. All right? So I'm illustrating to you right now cases 3 and 4 on the sheet of the transformations, right? X minus c shifts the graph right by c units. X plus c, f of x plus c shifts the graph left by c units. Okay, that's the relation of the original graph to the transformed graph. I forgot to say this on the sheet, but it's important. C is assumed to be positive. All right? So I am assuming that c is a positive number here, and that's why I have different cases, right? Other people might say, 1 and 2 are just one case. 3 and 4 are just one case, right? And there's subcases, positive or negative numbers. But I just wanted to make it all positive. So there you go. All right. And, you know, Desmos is fun. You could do stuff like do them both at the same time. See? Yeah. No? It's rudimentary screensaver, right? I don't know. You can make them go faster if you want. Anyway. All right. So what else could we do? What if instead of doing a square, we do a cube? What's that look like? See what x cubed looks like? And so the same story goes though, right? If I add, it moves it to the, if I add a positive constant, it moves it to the left. Put a negative constant, moves it to the right. If I add the number to it, it shifts it up or shifts it down, depending on whether it's positive or negative, right? Let's see here, what else? So let me get rid of all this. Try a different example.
Can we use Desmos for our testing?
No. There's no computers on the test. Let's see here. But what you can use Desmos for is to check your work. Like if you don't understand like what you should be seeing in your homework, this is something you can easily like load up and say, oh, this is what I should be seeing, you know. And also I'd encourage you to use it in other classes where you're not really being tested on math. You're just being, like you have a science class where you have to like understand how some formula works. This is a nice way to like plot that formula. Especially when you have a formula, a lot of times in science classes or other things, you might have a formula which has lots of parameters. This allows you to add those as sliders, and then you can adjust the parameters to see how like the graph looks if the parameter is different. It's actually very, very useful. Oh, okay, so how about absolute value of x? What's that look like? That looks like this, right? There's absolute value x. And what if we were to do, come on. Okay, I said, all right, there we go. Y equals, what if we do, say, minus absolute value x? What's that look like? See, so absolute value of x is going up. Minus the absolute value of x is doing what? It's going down here, right? So if we multiply the function by minus, what happens? It turns it over, right? What if instead of multiplying by minus, let's multiply by a constant. Let's say m, all right? So if m equals to 1, you multiply by 1, what happens? Nothing, right? That's why you can't see the graph, because they're superposed, right? Now if I make m a little bit, come on, if I make m a little bit bigger, see what happens if I put m equal to 2.3, what's it do? It stretches the graph vertically, right? Or you could think of it as compressing the graph. Let me show you what I mean. So there's two different ways to look at it, right? So if y equals m times the absolute value of x, right? You think of m as positive for the sake of our discussion, okay? Notice that you could also rewrite this as absolute value of mx. So this vertical stretch by m factor. This, on the other hand, is horizontal compression by m factor. So sometimes you could look at a given formula a couple different ways, like this one, right? I can either think of the green graph as being, stretching it vertically, right? Or I can be thinking of it as compressing horizontally. And that is an illustration of like 7 and 8 on this sheet, right? What happens if you have m between 0 and 1? Let's try that out. Like what happens here, m equals like 0.7, or here I'll go for 0.5. There. See what goes on? The original graph is in red. The transformed graph is in green. 0.5, it either compresses it vertically, right? So the opposite of stretching, it shrinks it vertically, you could say. Or it does what? It stretches it horizontally, because you can look at it either way. Any questions about this? No? Let's see here. What else could we look at? let's look at, put this away here, square root of x. What's that look like? Desmos is pretty smart, right? I just did SQRT. It made a square root show up, right? It's got a lot of nice pre-processing built in. It's pretty user-friendly. There's your square root, right? So that's, what is that? Do you guys understand what a square root is relative to other things we've done today? Let me throw something else into the mix here. So check it out, right? This is y equals x squared. This is y equals the square root of x. Do you see the relation between these two? Basically, you just take the red graph, the black graph rather, and lay it sideways, right? Just keep the upper half of it. That's exactly what the square root is. Square root is a half of a parabola turned sideways. That's what it is. All right, so so let's look at the square root graph. Let's use the square root graph to, excuse me. I had some sanding yesterday, and I always get some stuff in my lungs after I do that. I got a mask, but even so. All right, so let's illustrate transformation 6. And let's do 5 and 6 for this. So let's do 5 to start with. Y equals minus square root of x. Okay, so what do we got? Y equals minus the square root of x is the black graph. Let's see what that is. So this is called reflection over the x-axis. Pretty simple, right? If you put y equals square root of x and y equals minus square root of x together, what do you got? You got a whole sideways parabola, right? Actually, the totality of the red and the black graph here are exactly what it would be the solution set to x equals to y squared, for what it's worth. Okay, so great. That's minus the formula. All right. What happens if we put the minus on the inside? See what happens? I don't want that also to be red. Just a second here. You can adjust the color if you do the right thing. Come on. Ah, there we go. There we go. Let me get rid of the, I'm going to turn the black one off here for a second. So what we're looking at, the original graph is square root of x, right? If I look at y equals minus the square root of minus x, what happens is we take the graph and we flip over the y-axis. See that? So that's what happens when we replace x with minus x. That's that transformation, right? Now, we could try this with a more complicated graph, right? Let's try it with something like a little bit uglier. How about 1 divided by x plus 3. Right, so what happens if I replace x with minus x? Well, first of all, what happens if I just do minus 1 divided by x plus 3? What's that? See that? What happened? The original graph was red. The transformed graph does what? It just it reflects over the x-axis, right? So the red flips up to the green and down to the green, like that, right? And notice that in the reflection over the x-axis, what happens? The horizontal asymptote, which was where? The horizontal asymptote here was at 0, right? Y equals 0 is called the horizontal asymptote for this graph. Okay, the red one. There's also a vertical asymptote at x equals to 0. There's a y equals 0 is the horizontal asymptote. X equals to 0 is a vertical asymptote here, right? And both of those just stay put for this. Now, if we had if instead of being at 0, we can make the horizontal asymptote like, let's say 2. There you go. Now the horizontal asymptote is at 2. It's going to be a different story if we, come on, do that. Now it's a little bit complicated, but let me walk you through it. So what's going on here is the red graph has a horizontal asymptote of 2. See, this y equals 2 is the horizontal asymptote for the original red graph. x equals to 0 is the vertical asymptote. No, excuse me. Rather, x equals to minus 3 is the vertical asymptote. I'm sorry, guys. Minus 3. Minus 3 makes this 0. Okay? So we have x equals minus 3 is the vertical asymptote to the red. When we switched x to minus x, right? Excuse me, when we multiply the formula by minus 1, what does it do? That reflects over the x-axis. What happens then? The horizontal asymptote, which was originally at 2, flips to a new horizontal asymptote, which is now where? At minus 2. See, so it flips the horizontal asymptote over the x-axis down to here. What happens with the vertical asymptote for this function? Nothing. It just stays at minus 3, right? You flip the vertical asymptote over the x-axis, it just flips back to itself again. This story is going to be a little bit different if instead of doing... So right now we're looking at transformation what? We're looking at transformation 5, right? We're looking at transformation 5 for this 1 over x plus 3 plus 2 graph, all right? Let's now look at transformation 6 for this graph. How would I do that? Instead of putting the minus out front, where do I put the minus to do transformation 6? Where does the minus go? Not there, right? In the parentheses, right? It goes right there in the bottom in the denominator. All you had to do is replace the x with a minus x. Now we're looking at the transformation 6, the reflection across the what? Across the y-axis of this red graph. And you see what happens now, the horizontal asymptote at 2 stays put under the reflection. Now the vertical asymptote at minus 3 originally flips over here to 3 after the transformation. Right? Listen, the reason I'm doing all this is to try to convince you that I didn't just make up these 8 rules. That's really how it works. All right? Now we've seen some objective data using technology because it's like way faster than me doing these graphs by hand, right? I didn't expect you to, like write these down. I'm going too fast for that. I just want you to see it. Do we agree that these 8 steps are reasonable? They make sense? I hope so. So now that I have bullied you into accepting them, let's put them into practice with the worksheet. All right? So now we'll work on example 1, if I can put this away. So, I mean, yes, it is true that outside of taking a test in college algebra, there are better ways to graph, right? Just like outside of this course, if you have an algebra problem, you can hire a mathematician or an engineer or a school teacher to do that for you, right? But that's not what this class is about. This class is about trying for you to learn algebra. So the fact that there's an easier way to graph should not dissuade us from learning how to graph by hand. The reason that we want to learn to graph by hand is that it will actually make it so that you understand what the technology is telling you much more deeply. Being able to graph things by hand is the first step towards knowing when the computer is leading you astray. So I want you to have a sense of what does the graph of various formulas look like. I want you to have some sense of some of the basic examples without even having to consult technology. So on that sheet, there are 7 basic examples that we need to know, right? What are those 7 basic examples, the standard examples? Do you see them? I drew them out for you there. Yep.
I think mine was one of the ones that just had this. Do you want both of that?
Oh, you got that. So yeah, you're just missing the other sheet. Anybody not have the transformation? You definitely want the transformation sheet. You have it. So on the transformation sheet, right? Notice that I have standard examples. What are my standard examples? Parabola, cubic graph, reciprocal graph, volcano graph, ooh, square root graph, cube root graph, absolute value graph. All right, so these, we should know what these look like without having to go through the 20-minute process we did at the start of class, right? You should just have basically a sketch of that in your mind's eye. it shouldn't like be intellectually taxing to do that, okay? That's my point. If you don't know those already, then you need to memorize them. I say that, but is it true? Not exactly, because I do what? I let you have a formula sheet, don't I? So I suppose you can defy me, not memorize them, and just put them on your formula sheet. I can't really stop you because I said you get a formula sheet, right? So it's my own stupid fault for giving you that, but I'm not going to go back on that because I already said that, right? So, but really the fastest thing to do is to memorize these standard examples. Anyway, I think most of you probably know these standard examples already anyway. So let's go through example 1. So I'm going to make 4 graphs here. Those are supposed to be straight lines. I'm not doing too well here at the moment. So example 1 says graph what? Yeah, example 1. Y equals to, you say negative absolute value of x plus 3 minus 2. All right. So what I've done in each one of these examples is I've given you basically advice on how to do it. All right. So we're just going to walk through my advice. I'll warn you before we even get there, the advice for example 2 and the advice for example 5 is incorrect. So we're gonna have to change those. All right, I found those. But anyway, so let's focus on what works here. So the first step is, what is this graph? Like, what's the basic thing going on here? It is y equals to absolute value of x, right? So I start with y equals absolute value of x, right? So what's that look like? It's just a v, right? And if I want to keep track of this, it probably suffices to just track the origin, right? That's a point on the graph. Okay. Next up, what? I see I'm targeting for after that absolute value of x plus 3. So my next move is to look at y equals absolute value of x plus 3, right? And so what does that do? That is shifting the graph which way? How much? 3 units to the right or to the left? It's plus 3, so we'd move where?
To the left.
To the left. All right, good. I was trying to trick you, but you were paying attention, so I guess that's good. Although I don't know, I've mixed feelings. I like to trick students, but on the other hand, I want the students to understand. These are sort of competing goals. I guess I'd go with students understanding. It's more important than tricking students. Yeah. Progress over comedy, I suppose. Yeah. Now what? I want this minus, right? I want this minus, so next thing I add the minus. So I'm kind of, you know, building the formula, you know? So, and then one of the key ideas here is important to understand that the transformation process is one step at a time. And the order matters, okay? It's possible for a given problem there's more than one set of transformations that will get you to the desired end. But generally speaking, you can't just willy-nilly change the order of the steps. And the way it works is each step is the starting point for the next one. All right, so like going from here to here, I start this graph, right, to go to that graph. I don't look at this one, I look at this one. And so I have to flip this one. It's a minus, right? I'm taking the formula, I'm putting a minus in front of it. That is transformation number, where's my numbers? That's number 5, right? We're putting a minus outside the formula. So what that does, it just flips this guy upside down, like that. The vertex stays put, it's still at minus 3, 0, right? Okay, finally, where are we? Subtract 2, yeah? So y equals to minus absolute value of x plus 3 minus 2. So what we do is we take what we had before and we shift it down 2 units So the vertex goes from minus 3, 0 now to minus 3, minus 2, and like that. So there you go. That's the graph, roughly speaking. Right, and of course, I mean, for the final answer, let's make it nice, you know. We want to have our x going this way, we have our y going this way, you know, things like that. Maybe you want to add another point on your graph. What would the y-intercept be for the graph here? Like, what is this point right here if you wanted to add it? What would that be? Now we got to go back to the first 20 minutes of class, basically. Plug in 0, right? That's going to be the y-intercept. What happens when you plug in 0 to the formula? You get what? 0 plus 3, absolute value of 3 is 3, right? So we get minus 3 minus 2, that's at minus 5. So this point right here is 0 minus 5 for what it's worth, all right? Now, how many points should you add to the graph? Do I even need to add that point? Is that like written in stone? Is there some sort of like manual of college algebra point deductions where I say, oh, they didn't put a y-intercept in, I must take off points? No, right? I mean, this is just for your information. I'm showing you that we could add that point to make the graph a little bit more quantitative, right? Or we could have left it without it, and that would have still been a good answer. So if I say sketch the graph using transformations, what I did in the blue is sufficient. Now really, you know, the whole process we're going through today with examples 1 through 6, the truth is these are like, you remember when you first ride a bike, you had these training wheels, right? You don't want to keep those on forever, right? Because riding a bike is no fun if you've got the training wheels on, right? Unless you're just weird. I don't know. Maybe you like a trike, I don't know. But let's see, with training wheels, it's not even a trike, right? It's something else. But so we want to get past this eventually, right? So for example, let me show you how, let me just jump ahead for a second here and show you example 7. So example 7 is not even on the sheet. That's kind of my point. Think about this. I have y equals to 3 plus x minus 1 squared. So what is this? I'll do it all in one, right? I'm going to do it all in one. We start with y equals x squared, which is this, right? And then we're doing what? We're going over 1, and then up 3. So the graph is basically this. Right. In fact, eventually you want to get to the point where I don't even draw the black part. I just go straight to, oh, that is the parabola, y equals x squared, moved 1 to the right, and up 3. Right? So if the formula is sufficiently simple, you don't even need the like baby steps, right? You can just jump straight to the transform graph once you understand the method. Right? Now you may not be there yet, but after we do another 30 minutes of this, you should be closer to understanding example 7. Right? Here's another one. Example 8. So you got y equals 1 over x minus 3 squared. All right, so I look at that, I go, that's the volcano graph. And it's been shifted 3 units to the right. That's all it is. It's the volcano graph shifted 3 units to the right. The key feature of the volcano graph is it's got a horizontal asymptote of 0, it's got a vertical asymptote of x equals to 0. They're both, the x and y axis are asymptotes for the volcano graph. If I shift it 3 to the right, its vertical asymptote moves to 3. But otherwise, it's the volcano. So it looks like this. There you go. That's y equals 1 over x minus 3 squared. So more often than not, the application of this transformation of graphing idea is maybe just one step from a standard example, okay? Often I'm interested in just a one-step transformation from a standard example. My examples for class today are more complicated than that, all right? So as is often the case, I foolishly lead off with more complicated examples. As always, my goal is to confuse the students, of course, but that was sarcasm, just to be clear. I actually don't want you to be confused. So anyway, any questions about this so far? Let's go on to example 2 then. Again, example 2, I need to switch up. Steps 2 and 3 are bogus. I need to fix those, okay? So we'll deal with it as we get to it. All right, so example 2. I'm up against y equals the square root of 9 minus x minus 3. All right, so you guys tell me, what's the standard example at the heart of this example is what? Which is it? It's not absolute value, obviously, right? It's what? It's the square root function, right? So we start with that, right? What's that? Yeah, square root, okay. So we start with y equals square root of x, which looks like this, right? There we go. I'm going to track the origin just to keep myself sort of anchored to something. It's good to follow at least one point just to make sure you don't trick yourself. Okay, next up, what I did, and I'm not following I'm ignoring my sheet. All right, so steps 2 and 3 on the sheet, nonsense. Forget about those. What I'm going to do is I'm going to flip it like this, right? And so that's y equals square root of minus x. We actually looked at that in the Desmos here a bit ago, right? I'll do that. Okay. Oh, right now I need to use my imagination a little bit in the sense that, like, the formula as it's packaged I don't think is helpful. I need to rewrite the formula a bit and look at it this way. Square root of minus parentheses x minus 9, right? See, if I do that, if I re-image the formula like that, I can see how to get from here, right, to there. Because I'm replacing x with what? X minus 9. See, I'm making that substitution to get from here to there. See that? And so that, I understand, is a transformation shift right by 9, right? So where's my graph go? I forgot to label my origin. So that origin shifts over to here, 9, 0, and like that. Almost done. What's left to do? Finally, the formula. We don't quite have the right formula yet, right? One more step. We need to subtract 3, right? Subtract 3, finishing product here. Y equals square root of minus parentheses x minus 9 minus 3, which of course is the same as the original formula, just rewritten a bit. And so this is, we take the original one, we shift down 3, right? So the vertex of the parabola, sideways parabola, now shifts down to 9 minus 3, and we go like that, roughly speaking. That's not quite the right shape, right? The true shape is, you can look at the, there's a little bit of like a vertical tangent here, right? It kind of goes like that, to be fussy. But anyway, it's pretty good. Am I right to draw the line through the origin, like the finished product? Does that actually go through the origin? Is this point really here, or did I just get lucky or unlucky? Try it out. Plug in 0, what happens? Square root of 9 minus 0 is square root of 9. So you get 3 minus 3 is 0. In fact, this graph does cross the origin. So my final picture is actually about right. You know, if we had graph paper, we could do things more to scale. But I'm intentionally not giving you graph paper because the point here is not to like plug in numbers and do like the first 20 minutes of class. The point is to gain a qualitative understanding of the graph by shifting, reflecting. Yeah? So, any questions? So I switched up the orders step 2 and step 3 because I can't quite sort through what I have on this sheet. I tried to in the first time I taught it, and it didn't go well for me. So let's move on to example 3. See if I need to speed up or not. Oh, I need to speed up. All right, so I'm just going to do it. I'm going to do less talking, more writing this time, okay? Example 3, we've got y equals to 3 plus 1 over 2 minus x. So my first move here is going to be rewrite this as 3 minus 1 over x minus 2. That's easier to think about. All right? So this is pretty clearly a reciprocal graph problem, right? So I start with my reciprocal graph, which is y equals 1 over x. Okay, and for the reciprocal graph, what we want to do is we want to track the asymptotes. I think that's helpful. So the asymptotes for the reciprocal graph are just the x and y axes, all right? And it's got a horizontal asymptote of the x-axis, vertical asymptote of the y-axis, and this one, all right? My next move is to shift right by 2. When I shift right by 2, my new vertical asymptote is at 2. The horizontal asymptote stays put. And looks like this. Next up, I want to put a minus out front, right? So I do want to do y equals to minus 1 over x minus 2. What's that do? That flips it over the x-axis. If we think about flipping over the x-axis, the vertical and the horizontal asymptotes that I have, they stay put, right? We don't move either of the asymptotes with a reflection across the x-axis here. They just stay put. But the graph itself, though, it is flipping up here like so, flip down there like this. All right. And then finally, add 3. So adding 3 does move the horizontal asymptote. The vertical asymptote stays at 2. All right. So I still have my vertical asymptote at 2. But my horizontal asymptote moves from y equals 0 up 3 units. All right. So that's 3. And I may be escaping the little. Listen, these, you know, if I give you a problem on the test or the quiz with these 4 boxes, like, it's not written in stone that you have to put the graph inside the boxes. These are just a guide, you know, and if the problem leads you outside the box, so be it. And so like here, so the graph is this, roughly speaking. And there you go. So let me just to retrace our steps, all that really went on here is we took the reciprocal graph, we shifted it 2 units to the right, we turned it over the x-axis, and then we shifted it 3 units up. And that was it. So. Example 4. I'm going to skip. I want to do example 5. So if you want to see me